reduced row echelon form. Let's say we had a system of 3 linear equations. I could use an augmented matrix to represent this system. To write the augmented matrix, the first thing I do is create the coefficient matrix, which I do by looking at the coefficients of all the variables in all the equations. So for equation number 1, the coefficients of the variables are 2, 1, and 6. So that becomes the first row of my coefficient matrix. Row 2 would be 3, 4, 3. And then row 3 would be 1, negative 2, negative 4. And I augment that with the column of constant values that the equations are equal to. 7, negative 8, and 9. What I want to teach you how to do in this section is how to use elementary row operations to convert this augmented matrix into a matrix that's in reduced row echelon form. And the reason why we would want the matrix in this format is because it's easy to tell from that format if the matrix has no solutions, if it has infinite solutions, or if it has one solution, what that solution actually is. And any matrix that is in this format has a structure that follows 5 rules. Number 1, if there are any rows of the matrix that are all 0, they're at the very bottom of the matrix. Each leading entry is in a column to the right of the leading entry above it. So if we look at row 2, its first non-zero number, its leading entry, is right here. It's this 1. Notice that leading entry is in a column that's to the right of the leading entry that's above it. And number 3, all entries in a column below a leading entry are 0. So if we look at the leading entry from row 1, everything below it is a 0. Now any matrix that follows those first 3 rules is in what we call row echelon form. But for a matrix to be in reduced row echelon form, all the leading entries also have to be a 1. Notice they're all 1s. And each leading 1 is the only non-zero in its column. So looking at the leading entry from row 2, not only is there a 0 below it, but there's also a 0 above it. It's the only non-zero number in its entire column. And to get a matrix into this reduced row echelon form, there is a process called Gaussian elimination that we're going to follow. So let me start by copying this augmented matrix down here, and we'll start doing some elementary row operations. Now the first thing we want to do is begin at the leftmost non-zero column, so right here, and make a non-zero entry, the pivot at the top. Well, all of the entries in this column are non-zero, so we could use any of them as the pivot at the top. But I notice in reduced row echelon form, eventually I'm going to want a 1 there. So we might as well make this one the pivot at the top of that column. So to get that 1 to the top of the column, we'll have to swap this entire row with the row that's at the top. So in order to get this 1 up to the top of the column, we can swap all of row 3 with all of row 1. So this 1 is now called our pivot. And what we want to do next is make all of the numbers below that pivot, so the 3 and the 2, we want them to be a 0. I'll have to do that using the replacement operation. I'll start by making this 3 become a 0. I could do that by replacing all of row 2 with row 2 minus 3 times row 1. So row 1's actually staying exactly the same. I'll leave it as it is. But I'm replacing all of row 2 with each of these entries minus 3 times those entries. And now I also want this 2 to become a 0, so I can replace all of row 3 with row 3 minus 2 times row 1. Now that we've created zeros below our first pivot, we're going to ignore the first row and repeat that same process for the remaining submatrix. We're going to look at the first non-zero column. We're going to make a non-zero value be the pivot. I might as well let 10 be the pivot. And then make everything below that 10 become a 0. So I just need to make this 5 become a 0. We'll continue doing that down below. Continuing with this matrix, I can make this 5 be a 0 by replacing all of row 3 with 2 times row 3 minus row 2. We could now get our answers by writing the 3 equations that these rows correspond to and using back substitution to get the answers for the variables. But we're going to continue on to get this matrix into reduced row echelon form to make it more obvious what the answers are. So what I have to do now, going from right to left, is create zeros above each leading entry, and also make the leading entries all be 1. Looking at row 3, it would be easy to make this leading entry be a 1 just by multiplying all of row 3 by 1 over 13. Let me make a little bit more room so I have space to work. And what we want to do now is make the entries above this leading one. We want these entries to both be 0. So I'll leave row 3 the same, but I'll replace row 2 with row 2 minus 15 times row 3. And now I'll change this negative 4 into a 0 just by doing row 1 plus 4 times row 3. Let me zoom back out, and let's now make this 10, which is the leading entry in row 2, let's make it become a 1 by multiplying all of row 2 by 1 over 10. So I'll continue that down here. And the last thing we have to do is get the number above this leading 1 to be a 0. So this negative 2 has to become 0. I could do that by replacing row 1 with row 1 plus 2 times row 2. And now this matrix here actually reveals to us the answer to this system. Remember, this part of the system is the coefficient matrix. Those columns represent the coefficients of the variables x, y, and z. So each of the 3 rows corresponds to an equation of our system. The first row of our matrix tells us that 1x is equal to 3. The second row tells us that 1y is equal to negative 5. And the third row says that 1z is equal to 1. So our system of linear equations has one unique solution, but that's not always the case. Let me give you a couple examples for what the reduced row echelon form could look like that would indicate to you that this is not the scenario. So let's erase what we have above. So this scenario is when there is one unique solution. And the system is often called an independent system if there's one solution. But let me also show you what it would look like if there were no solutions or infinite solutions. Let me start by drawing a matrix that's in reduced row echelon form that has no solutions. I know this matrix would indicate that the system has no solutions by looking at row 3. Based on row 3, I see that 0 would have to be equal to 1. And I know that 0 cannot equal 1, therefore there are no solutions to that system. But what about infinite solutions? Let me draw a matrix that represents that scenario. Based on the coefficient part of this matrix, I can tell there are 3 columns, so there must have been 3 variables in the equations. I'll call them x1, x2, x3. But when I look at the number of leading ones in my matrix, I see there are only 2 leading ones, but there are 3 variables. When you have more variables than leading ones, we know there's going to be infinite solutions. And if I were to try and write the solutions, from row 1, I can see that 1x1 plus 2x3 is equal to 3. And if I were to rearrange that to isolate x1, I can move this 2x3 to the other side. And from row 2, x2 minus x3 is equal to 4. And I could rearrange that to isolate x2. And in the column for x3, there are no leading entries. 2 is not a leading entry, negative 1 is not a leading entry, and 0 is not a leading entry. Which means that x3 is what we call a free variable. So you could pick anything you wanted for x3, and then based on what you pick for x3, that's going to alter your answers for x1 and x2, which is going to create an infinite number of answers that'll satisfy your original system of linear equations.